Hi girls, just coming back to you and taking a look at some of those math questions that you'd asked me for. Just wait now, and I'll have it up on screen for myself. And I'd advise you to do the same, girls, and just have the questions up in front of you now. It'll make life a little bit easier for you. So the first question that somebody came back to me and asked me was, two people came back and asked me to look at the BOD, which is question 9b. At least that's the only version of the BOD I could see. It was an unusual way to ask it, but it made use of all the stuff you already had. So it talked about 50 centimetres of water being diluted to a litre. So the first thing I would do is, that's like ethanoic acid or bleach. What's my dilution factor? So I took it to from 50 to 1000, so 1000 divided by 50, I diluted it by 20. Okay, so whatever these figures are that they're quoting, they're 20 times stronger in the actual water, because you diluted it by 20. So if they're saying 9.8 parts per million, that should be multiplied by 20 to find out what a litre of the actual water would have had. So it said immediately after doing the experiment with 9.8, then they stored it for a while and went to 2.6. And the maths part of the question, which is the second part, says calculate the BOD of the undiluted stream water. So that is before you touched the stream water. Okay. And they're asking you to calculate the pollution. Well, the difference between these was the pollution, because 2.6 means that everything that was in there, all the microorganisms that were causing the pollution, that were causing the BOD to be thrown up higher than it should have been, are all now dead. So if you store the water in the dark environment for days on end, anything that's living in the water is going to die. So the difference between them is what the level of pollution was. 2.6 is the bare minimum, so that is what the natural water would have. So the difference between them is what the pollution was, so that's 7.2 parts per million. But now we have to ramp it back up to where it was. So we remember to ourselves that the original sample was diluted by 20. So 7.2 is actually 20 times less than it should be. So I've got to multiply that figure by 20 to figure out what it was in the undiluted 50 centimetres cubed of stream water that they originally got. It is an unusual way to ask the question, because normally when you do BOD, you collect a litre of the sample, which is what we did. I went out and collected a full 2 litre bottle or a litre bottle. So you don't normally dilute the water. But if you look at that calculation again, really what it's asking you to do is, can you make the link between this one and ethanoic acid? Because you do dilution factors in other chapters. Okay, so that's the question 9b in the calculation. Any more problems, let me know. And the next one somebody asked me for was question 7. So I'll run through question 7. I assume Stateless-Lattius principle is not a problem. What's the name given to the industrial process? Is the Haber process. Write the equilibrium constant, which is the Kc, again square brackets being most essential. So on the top of the line it'll be NH3 squared divided by NH and H2 cubed. But they'll be in square brackets. But I assume it was the calculation that was the issue. So here's the calculation. Okay, so it tells me initially I have 4.5 moles of this, 13.5 moles of this. Okay, and obviously at the very beginning I had no product, because I haven't started yet. At the end it tells me I have 3 moles of this product. Okay, so if we start with the ratio is 1 is to 3 is to 2. So 2 parts of the ratio is now equal to 3 moles. Okay, so what I do is 2 parts is equal to 3 moles. 1 part, which is what I'm using here, is half that. So it's 3 divided by 2 is 1.5. And then multiply that by 3 to get the 3 parts, because I'm going to have a 3-parter as well. And that's all based on that balanced equation and your understanding of the ratio 1 is to 3 is to 2. So then what I'm saying is, at the end I have 3 moles of this. So I must have lost 4.5 moles of this, because 13.5 minus the 3 parts, 3 coming from here, is 4.5. And then it's 4.5 moles minus 1.5, because that's 1 mole or 1 part. Okay. Why am I dividing across by 2? It told me it was in a 2 litre container. So you have to have this as moles per litre. So in moles per litre it's 1.5 moles per litre, 4.5 and 1.5. Sub them into the Kc then, so it's the product squared divided by the first reactant to the power of 1 and the second reactant to the power of 3. And again, the 3 and 2 is coming from this balanced ratio. And then the answer is 0.01646. They rounded in the marking scheme, but we don't round them. We keep them to 4 or 5 decimal places. Okay. Again, any questions on question 7, girls, in terms of the calculation, come back to me. I've given you the marking scheme. The other ones is name the catalyst, state and explain the conditions of temperature and pressure to maximise the yield. We've done that yield several times. Okay, so again, to maximise it, it's at low temperature and high pressure to maximise the yield, but they actually can't use too high a pressure, and too low a temperature would slow it down too much. So the conditions that they actually use are relatively high pressure, like 300 atmospheres or 400 atmospheres. They can't go higher than that because any higher is a safety concern. And the temperature they use is well above a low temperature, so it's about 300 degrees Fahrenheit, and the reason they do that is to increase the rate of reaction. Okay. The next question then that you asked me to take a look at was question 6. So again, I think it was yourself, Lilibeth, and that asked for it. I assumed it was the calculation, but I could be wrong. You might be looking for something else out of it, so tell me if there's something else that I'm not seeing. But the calculation is here. So this was given to you, but straight away when I see this calculation, I think to myself, well, the definition for heat of combustion or heat of formation is when 1 mole. So instantly that's 2. So that's going to be a problem. They gave me this one. They told me the heat of combustion of carbon, so carbon plus oxygen is CO2, and burning hydrogen in oxygen gives you water, and you need a half there. Okay, what am I looking for? I'm looking to make C8H18. So that's 8 carbons and 9 H2, because hydrogen is naturally found in the formation of H2. Okay, so what do I need? Well, I need C8H18. I only need one of them, and I need it to be on the right hand side. So equation 1, it's on the wrong side, so I need to reverse it and bring it over here. And I also need to divide it by 2 because I only need one of them.